So speaking of ʻōkalele ʻaneʻauna, I'm actually going to start with the verse dedicated to Amakihi from that holy. ʻOkalele ʻaneʻauna o kahakaʻi ala lani o hoʻonohono o a paʻapakaʻaina o Hawaiʻi kua uli o hualau ka ma kua puka chronically he manu ʻaina lele. E ia aʻe ka Amakihi manu kupaina hou uka. Manu holo nape nape, Amakihi kaulana I ka hoʻōla maʻi. Ika ia mai ke kula nui o Manawa, a I pele kunu ma Molokaʻi. Mai kalapana ai makuʻu mapuna. Hana ka Amakihi kani, kia I ia e ka mamanohui kai. O la a moloi kau helo nohui uka. O ka Amakihi ana lele a paʻapaʻahia. And all together we can go. Mahalo.
Great.
Mahalo nui everyone for being here today. And mahalo to ʻOkalele ʻaneʻauna, or to Ahui Manu for writing ʻOkalele ʻaneʻauna, and ke kuhi ke aliʻi kanaka ole o Haiulani for leading that group. They're a group devoted to raising awareness of our bird people here in Hawaii and giving our aloha to them. So mahalo to them for giving us this chance to use out in the field, and also for giving me the opportunity to bring them into this space now. So I wanted to start with just a little bit of background about me. Pat gave a pretty good introduction, so I won't go too into it, but I am born and raised in Westfield, New Jersey, not too far outside of New York City. And from a really young age, I had a deep love for animals. I grew up with rabbits and a dog. And before I had those pets, I was collecting caterpillars and spiders and all kinds of things that I found in my house and naming those. So I think my parents got me a rabbit to get me to stop doing that. But in addition to my love for animals, my family also went to a lake up in Maine every year, the Three Corner Pond. And this is really the first place that I felt connected to a space. And going back and visiting that place every year was really a big part of why I started caring about the environment and seeing those changes in that place, seeing the lake level shrink as climate change wreaked more havoc on the area, and seeing the forest torn down really fueled my passion for conservation. So cut to college, I went to Lafayette College for biology. I actually went in being pre-vet, but I ended up joining a bird lab with Mike Butler over at Lafayette. And once I realized that being a vet was not the only way to work with animals and that field research was a career option, I stuck with it and really never looked back. And then I graduated in late 2019, pretty much straight into the pandemic. So I ended up working in a COVID lab for a year before I moved to Florida to do marsh bird surveys. And then I ended up connecting with Pat Hart out here and coming to move out to Hawaii 3 years ago in 2021 to pursue my master's. And truly, it has been one of the greatest honors and privileges of my life to be out here and learn from people here. I have always been driven just by a deep love for the earth and for the other species that we share this planet with. And so it's been really amazing to come here and learn from other people who really share those values. So that's enough about me. Let's get into the birds. Hawaii is home to a vast diversity of endemic forest birds. About 5.5 million years ago, some rose finches were blown off course and landed in Kauai. And from there, they speciated rapidly, moved across the islands, and evolved into about 55 different species of honeycreepers. They're of great cultural importance to the people of Hawaii. Bird feathers, or hulu, are traditionally used to adorn ali'i, or royalty. So they're used for kahili, which are these staffs with feathers on them, hoʻōla, which are capes or cloaks, and mahiole, which are the helmets that adorn the ali'i. These birds are also of the utmost environmental importance. Around the same time that this adaptive radiation of honeycreepers was happening, there was also this adaptive radiation of lobelioids, or this family of plants that is endemic to Hawaii that also came to Hawaii and rapidly speciated. And so you can see in this picture on the left how similar the shape of these honeycreeper bills are to many of these lobelioid flowers with that long tubular shape. And unfortunately, that top bird, Drapanis pacifica, the mamo, is no longer extant. They have gone extinct in the wild. But you can see how closely those two match up to each other. And so the birds are heavily dependent on these lobelioids for their food source. And likewise, the lobelioids, such as cyanea, or commonly known as haha, are heavily dependent on the honeycreepers. Unfortunately, in recent years, there has been a mass amount of population decline in our honeycreepers. Of the 55 honeycreepers that evolved here in Hawaii, only 17 are still surviving in the wild. Threats to these honeycreepers include habitat loss, introduced predators like cats and rats, and diseases like avian pox, mange, and avian malaria. This is a quite depressing graphic showing all of that. So perhaps the greatest of these threats is avian malaria. Avian malaria is a protozoan parasite that targets the liver and red blood cells of its host. It's referred to as Plasmodium relictum, scientific name. And it's carried by southern house mosquitoes, which were introduced to Hawaii around 1826, Culex concapaciatus. And the first documented case of avian malaria in a Hawaiian species of bird was around the early 1900s. And since then, it has led to the extinction of many of our native forest birds. And many of those that remain are largely threatened. So some intense consequences can come with acute infection, which is when the level of parasite is highest in the blood of these birds. So acute avian malaria may cause weight loss, anorexia, which is when a bird stops eating, related to that weight loss. Also enlargement and discoloration of the liver and spleen, again, since this parasite specifically targets red blood cells and the liver. Also anemia, which is essentially extreme lethargy that comes when not enough oxygen is circulating through the body. And in the worst cases, mortality. Currently, mosquitoes are restricted to lower elevations below 1,500 meters. But with climate change and rising temperatures, they're predicted to move up in elevation. Presently, birds in Hawaii have these high altitude refugia that are disease-free because the mosquitoes can't breed past that elevation. But as temperatures rise, they may lose these high altitude refugia, and the threat of avian malaria will become much greater. Currently, you can only see many of our endangered species like Ākepa above that mosquito line, where the threat of disease is not as imminent. On islands like Hawaii, they no longer have these high altitude refugia. And so that's why we're seeing such stark population drops on those other islands. So all of this is pretty bleak. I don't want to completely depress you. So enter the Hawaii Amakihi, which is kind of a beacon of hope in the conservation field right now. Hawaii Amakihi, our Chlorodrepanis virens, are a generalist honeycreeper predominantly found in Ohia dominant forests, mesic to wet. And they, for whatever reason, seem to be more resilient to avian malaria. They have established populations below that mosquito line, as low as sea level in Puna, and are even found in Molokai. So to give you some frame of reference of how Amakihi compare to other honeycreepers here in Hawaii, their mortality rate from avian malaria ranges from 2.5% to 65%. This range is pretty broad, but it heavily depends on the elevation at which these populations are found. So lower elevation populations of Amakihi tend to have lower mortality rates than higher elevations or higher elevation populations of Hawaii Amakihi. But like I said, Hawaii Amakihi can be found as low as sea level in Puna, although they're typically found above 300 meters in elevation. As a comparison, ʻApapane, another Hawaiian honeycreeper, have a mortality rate of about 63% on average. And they're rarely found below 250 meters in Puna, but typically they're also found above like 1,000 meters or so. And ʻIʻiwi are the worst hit of the bunch. They have a mortality rate of about 90%, and they're rarely found where the mosquitoes are mostly present, so they're rarely below 1,250 meters. Sometimes there are stragglers that go below that elevation, but they're so likely to die from disease that it prevents them from forming robust populations. So Amakihi who survive acute infection have the benefit of having these avian malaria antibodies. And so if they're bitten by another mosquito that carries Plasmodium relictum, they're more likely to avoid that acute stage of infection. So they won't get a really intense infection again. So Amakihi that do survive acute infection maintain both these avian malaria antibodies and this low level of parasite in their blood that allows them to develop those antibodies. So this is one of those benefits, preventing that future acute infection. However, having that low level of parasite in your blood potentially for the rest of your life might come with some costs. This hasn't been heavily studied here in Hawaii, but studies of chronic infection in other birds have found reduced energy stores. This can show up as reduced triglycerides or reduced fat stores. Also reduced hematocrit and hemoglobin. These are both related to red blood cells. So hematocrit is the proportion of whole blood that is red blood cells, and hemoglobin is the protein binding, or the oxygen binding protein in red blood cells. And so both of these are related to oxygen circulation throughout the body. So if you have lower levels of hematocrit or hemoglobin, you're getting less oxygen circulating through the body and are more prone to anemia or that extreme lethargy. Chronic infection can also come with an increased rate of telomere loss. Telomeres are those caps on the chromosomes that basically protect your genetic material. And so an increased rate of telomere loss can be associated with an increased risk of age-related diseases. Other side effects can include reduced activity levels. So this could mean eating less, or perhaps reproducing less, or not defending your territory quite as much. And although reproductive success can be reduced in other birds, this has not been found in Hawaiʻi Amakihi. In fact, a study of reproductive success in Hawaiʻi Amakihi found that nesting success was higher in pairs with chronically infected males than in pairs in which males were uninfected. So my goal for this study was to elucidate some of those long-term effects of chronic avian malaria in the Hawaiʻi Amakihi. And so my first objective with this was to assess the physiological status of Amakihi with chronic avian malaria. And with this, I hypothesized that chronically infected Amakihi would suffer greater physiological costs than uninfected Amakihi. My second objective was to determine the concentration of Plasmodium relictum in the Amakihi blood and how that influences physiology. So my hypothesis with this was that as the quantity of Plasmodium relictum increases in the blood, the physiological condition of Hawaiʻi Amakihi would worsen. So how exactly do you gauge physiological condition? There's a whole plethora of variables that feed into the physiological fitness of an animal. I decided to go with 4 variables that I thought would be most relevant for chronic avian malaria infection. So the first of these is hematocrit. Again, that's the portion of whole blood that is red blood cells. And because avian malaria specifically targets red blood cells, I thought this would be a relevant factor especially. I also looked at oxidative damage. Basically, when your body attacks a foreign agent, it uses these reactive oxygen species, but in the process of trying to attack a foreign agent, it also attacks itself and causes tissue damage. And so oxidative damage is a measurement of that. Oxidative damage can also result from a parasite creating reactive oxygen species and attacking the body itself. I also looked at triglycerides, which are a good indicator of nutrient levels in the birds. Typically, if they're eating more, they would have higher triglycerides. And I also looked at body mass. Generally, heavier birds are healthier birds. And so with all of this together, I would expect worse physiological condition to look like lower hematocrit, higher oxidative damage, lower triglycerides, and lower body mass. So this study was carried out in Kauwehu, which is presently known as Āinahou Ranch in Hawaii Volcanoes National Park. It's in the Moku or district of Ka'u in the Ahupua'a of Keauhou. It's at an elevation of about 1,050 meters, which is a middle elevation site as far as Hawaii goes. It's an Ohio dominant mesic forest, and chronic avian malaria was present in about 32% of Amakihi here. So it seems that there's a pretty high infection rate at this site. Before I go on, it's important to acknowledge that this site is Kanaka Maoli land. Keauhou is sacred, Keauhou especially is sacred land because Halema'amba'u is located there, the dwelling place of Pele. And so it's important for Kanaka to be able to access this land without charge, as they have dwelled in and nurtured this land far before its establishment as a national park. Avian malaria is a direct consequence of the ongoing illegal occupation of Hawaii. It is our kaulana as stewards of this land to not only fight against avian malaria, but also to counteract this continuing colonial legacy by supporting Hawaiian cultural practices like speaking ʻōla Hawaii and returning land to Kanaka Maoli. So I wanted to get us rooted in this space by giving you all some history of ʻainahou. Ka'u is known in Olelo No'eau as Ka'u Makaha, or Ka'u of the fierce fighters. The people of this land are really known for their strength and endurance. Ka'u is not an easy landscape to navigate. It's very harsh. There's lots of lava flows, not a ton of farmable land. And so the people of Ka'u are known for their ability to not only survive, but thrive despite these hard conditions. The people of Ka'u are also known for their tendency to rebel against oppression, which is also how they get that legacy of Ka'u Makaha. In the ahupua'a of ʻainahou, there is a trail that runs through it, Mauka to Makai, to distribute resources across the ahupua'a. This trail is no longer in use, but it does run directly through the ʻainahou area. At one point, the birds of Ka'u were so abundant that kia manu, or the practice of catching birds to create those leihulu, or adornments for ali'i and other royalty, was common practice. Upon European contact and the introduced diseases that came with it, the Ka'u population dropped from about 10,000 Kanaka to just 3,010 by 1847. So it was not just the birds of this area that were impacted by introduced diseases, but the Kanaka as well. In addition, the pulu trade. Pulu are those golden ferns at the base of hapu'u, or tree fern fronds, and they were used to stuff mattresses and pillows and things of the like. So that was a big trade in the early 1800s, and that, along with cattle grazing, led to widespread habitat destruction in that area. So how did Kauehu become ʻainahou? ʻainahou was originally an ilikapono, or smaller land division, in the ahupua'a of Kapapala. However, in the 1848 Maheleʻaina, in which land districts were redrawn, ʻainahou and Kapapala were split. And the Makai section, or the shoreward section of ʻainahou, was gifted to Victoria Kamamalu, who was granddaughter of Kamehameha I. This land was passed down through the Kamehameha lineage for a while, and then inherited by Princess Bernice Pauahi eventually. In 1884, Princess Pauahi died, and her husband, Charles Bishop, who I'm sure his name you're familiar with, sold all of ʻainahou except for Kauehu to the US Congress. And so most of ʻainahou was used later in the establishment of Hawaii Volcanoes National Park in 1916, excluding this Kauehu area. Kauehu was leased by a number of different owners, changed many hands for a while. But it seems that somewhere around 1897, it was renamed to ʻainahou by William Shipman. Accounts from J.S. Emerson recalls visiting William Shipman's ranch, Kauehu, lately named ʻainahou. Eventually, Shipman's son, Herbert Shipman, became the leaser of the land, and he built the Ādinaho Ranch House in 1941. This ranch house was largely used to raise cattle to provide meat for soldiers during World War II. But it was also used for Shipman's horticultural endeavors. He was a botanist by trade, and so he grew many ohia trees as well as many introduced plants. So now that we all know a bit more about the space, I will let you know what we did there for this study. So sampling for this study was conducted every other week between May 2022 and August of 2023. We set up mist nets at the beginning of each day, typically 8 to 11 mist nets, depending on the day and how many people we had. And mist nets were 12 meters to 18 meters long. We caught birds in the mist nets and then carefully extracted them for processing, took them back to the banding station. Next, we banded new captures with a USGS aluminum band. We measured the tarsus, bill, and wing length. For those of you not familiar with bird anatomy, the tarsus is basically this foot bone on their leg. So if you're looking at this and this is all the toes, this is the tarsus from the ankle bone to the top of the toes. We then determined the age. We grouped age categories into juvenile, formative, and definitive plumage. Juvenile birds were hatch-year birds. Formative birds were late hatch-year and early second-year birds. And then definitive plumage were either late second year or largely after second-year birds. I ended up excluding juvenile birds from my analyses because none of the juveniles at this site were infected with avian malaria. We also sexed each bird based on their plumage, size, and breeding characteristics. For breeding characteristics, we were looking for a brood patch. So for Hawaiʻi Amakihi, only the female incubates the eggs, and they develop this thing called a brood patch, which is when they lose all of the feathers, well, not all of the feathers, but a good amount of feathers on their breast. And that allows for increased heat transfer to the eggs while they're incubating. And we also looked for a cloacal protuberance on the males. That's basically when the cloaca swells as it fills up with sperm. So next up, we took a 75 microliter blood sample from each bird, sometimes a bit less, but never more than that. And then we weighed each bird, gave them some Necton, basically their lollipop of sugar water after their doctor's visit, and released them. And you can see this was a recap on the right, and they know exactly what they're getting and they can't get enough. Sometimes they don't even want to leave. At the end of the day, we took the blood samples back to the lab, centrifuged them down to separate out the plasma and the red blood cells. I get distracted too. They're so cute. And then we we measured the total amount of blood and the amount that is red blood cells. That's what allowed us to measure hematocrit. And then we extracted the red blood cells, added 600 microliters of blood buffer for storage, and stored them at -20 degrees Celsius. We also separated out the plasma and stored that at -80 degrees Celsius. Next step was to quantify the level of parasites in each bird's blood using qPCR. So we first extracted the DNA from the blood samples using a DNase blood and tissue kit. In order to do qPCR, we use GRW4 specific primers that target the cytochrome B gene in Plasmodium relictum. So basically, these primers are looking for genetic sequences that are specific to the avian malaria parasite, so that only that DNA is getting amplified in these samples. Samples were run in triplicate for Plasmodium DNA, and then we ran each sample once more for bird DNA. That way we were able to ensure that any birds that were showing up negative for Plasmodium relictum didn't just have no DNA at all and something went wrong in the extraction. We then mixed the samples with the probes and primers and put them through 50 heating and cooling cycles to amplify the DNA. A lot of this was done by Carly Stein, so I must give her a shout out. She was the qPCR queen. And then at the end of this, we got a CQ value for each sample. If the CQ value was 0, that means that no DNA amplified. And so the malarial status is undetermined, meaning they're either negative for avian malaria or their levels of Plasmodium are so low that it wouldn't be picked up by qPCR. And then if the CQ value was between 20 and 50, the bird was considered positive or chronically infected. I will note here that there were some values that were borderline acute infection, but where exactly that cutoff between acute and chronic infection is still sort of being determined. It's actually an ongoing topic of study at the Ādinahou project. So I had a few birds that maybe could have been considered acute, but they weren't outliers in the data set, and so I decided to include them as chronic. Next, I measured oxidative damage. This is the tissue damage that results from an immune response. So I used the DROMS test from Diachron International, which measures reactive oxygen metabolites, or ROMs, in the plasma. Reactive oxygen metabolites are basically the result of that tissue damage. So reactive oxygen species are what attack the tissues, and these reactive oxygen metabolites are what result from that tissue damage. I ran the samples in duplicate and mixed them with a reagent that creates this pretty pink color. Basically, the amount of pink in these samples is directly proportionate to the amount of reactive oxygen metabolites. And so I measured absorbance at 492 nanometers to calculate the ROMS concentration. And this gave me values with units in UCAR. Basically, 1 UCAR is equal to 0.08 milligrams of H2O2, aka a hydroperoxide, aka an reactive oxygen metabolite per deciliter.
Yeah, get rid of my face too.
can I do that?
Yeah.
Okay.
Perfect.
Quick house cleaning with talk. So next up, I measured triglycerides, which are, again, a good indicator of nutrient levels in the birds. And they're also an important covariate for DROMs. Basically, DROMs are measuring damage to lipids, so it's also important to measure the total lipids to get an idea of what that relative damage is. For this, I used the lab assay triglyceride kit from Fujifilm, and I ran samples in duplicate once again. Samples were mixed with this reagent that made this pretty blue product. And again, the color of blue, or the intensity of that blue, is proportionate to the amount of triglycerides in the sample. I measured absorbance at 595 nanometers to determine the concentration of plasma triglycerides. And units for this were given in milligrams of triglycerides per deciliter. Now, my favorite part of the whole thing, the stats. I ran models for each of my physiological variables in R. I created a separate model for each parameter. So first, looking at hematocrit, I created a global model for hematocrit that included hematocrit as the response variable, disease status as the explanatory variable, and then sex, age, and breeding status as fixed effects. I included these as fixed effects because older birds tend to have greater hematocrit, at least to a point. Also, males tend to have higher hematocrit than female birds. And breeding birds tend to have lower hematocrit than non-breeding birds. This is largely due to a phenomenon known as reproductive anemia, whereby the females, when laying an egg, produce lots of estrogen, and that estrogen inhibits red blood cell production, and that can lead to anemia in these birds. So I created these models, and I used model selection in R to determine which were the top based on that global model. So this table is showing those top models. I also included the global model, regardless of if it was one of the top models or not. So that's bolded here. And I also included the null model for reference. So with this table, the most important thing to look at is that AICC value. That's showing the quality of the model. Generally, a lower AICC value is better. And I included within my group of top models any that the AICC or delta AICC was less than 4. So in this case, I had 4 top models for which that delta AICC was less than 4. And then I used those 4 models to create an averaged model, and that's what I used for my analysis. Next, looking at triglycerides, I used log transformed triglycerides to achieve a normal distribution. And so that log transformed triglycerides was my response variable with disease status as my explanatory variable. And in this case, I used age, sex, breeding status, and time of day as fixed effects. For birds, females tend to have higher triglycerides than males. Adult birds tend to have higher triglycerides than younger birds. And also breeding birds tend to have greater plasma triglycerides. This is where the metabolism bit gets a little confusing, but basically breeding birds might be catabolizing more fat reserve or metabolizing more fat reserves to create energy for breeding. And so they might be losing weight, but they'll have more triglycerides in their plasma. So there's a lot happening with the metabolism here. I'll try to sum it up as best I can, but to start to get into that. And then I also included the time of day because there's a well-known phenomenon with birds whereby triglycerides are lowest in the morning because the birds have been fasting all night, they haven't been eating, and then the triglycerides increase throughout the day as the bird eats more. I also included the interaction between sex and breeding initially, but I removed it because it did not prove to be significant. And so this gave me 8 top models, and those were the ones that I used for my average model. Next, looking at oxidative damage, I square root transformed oxidative damage to achieve a normal distribution. And then I use that square root transformed oxidative damage, or ROMS, as my response variable, disease status as my explanatory variable. And in this case, I included fixed effects of age and breeding. Breeding birds tend to have higher oxidative stress, as do adult birds. And while there are often sex differences in oxidative stress in other species, sex did not hold any weight in the top models in this case. And so I removed it from the global model altogether. And so this gave me 7 top models that I included in my average model. Lastly, looking at body condition, basically because mass is a function of body size, it's important to relativize mass for the analysis in order to get a better idea of what the actual body condition is. So I created this variable of body condition by dividing the body mass of each bird by their wing chord, which is a good metric for body size. With this, I use that body condition variable as my response variable, disease status as my explanatory variable, and then I use sex and breeding as my fixed effects. And in this case, I got 3 top models, but because my global model proved to be the highest, that was the model that I used for my analysis rather than an average model. So lastly, I did correlation analyses for each of these parameters, looking at the relationship between CQ value and physiology. So I used the core.test function in R, and I did this for only infected birds. So all of those 0 CQ values were not included in this analysis. So that's enough stats. Let's get into some results. First, looking at disease status, there was no difference between positive and undetermined birds in terms of their hematocrit levels. So it seems that if there is any damage to red blood cells that results from chronic infection, the birds are able to offset it, perhaps by ramping up their red blood cell production. So it seems although acutely infected birds do face anemia and lower hematocrit levels, that same does not hold true when they're in the chronic stage of infection. I did, however, find sex differences in hematocrit. Male birds generally had higher hematocrit than the female birds. This does align with previous studies looking at sex-based differences in hematocrit, so this was not necessarily a super surprising result. Lastly, looking at that correlation analysis, there was no correlation or relationship between CQ value and hematocrit. And so this suggests a level of tolerance for the Hawaiʻi Amakihi. Even as that intensity of chronic infection is changing, their hematocrit levels stay the same. Next, looking at oxidative stress. I first wanted to show the correlation analysis between triglycerides and reactive oxygen metabolites. So you can see that as triglycerides increase, reactive oxygen metabolites also increase. This is a pretty well-known phenomena. If you have more lipids in the body, you're more likely to have more damaged lipids as well. Next, looking at disease status. Although reactive oxygen metabolites were slightly higher for positive or chronically infected birds than for uninfected birds, this relationship was not significant, or this difference was not significant. And so it seems that even if there is some pro-oxidant activity coming from either the parasite or from the Amakihi immune response to that parasite, they're able to offset it by circulating more antioxidants. Or perhaps there's just not more pro-oxidant activity from that chronic infection. So that would be worth looking at more. And then looking at that correlation analysis, again, there was no relationship between CQ value and reactive oxygen metabolites. So this suggests a good amount of tolerance in terms of oxidative damage as well. Even as that intensity of chronic infection changes, the reactive oxygen metabolites stay the same. Next, looking at triglycerides, I first wanted to show that relationship between time of day and triglyceride levels. The same trend holds true as it does for many birds, where they have the lowest levels of triglycerides in the morning, and they increase throughout the day as they're eating more. Next, looking at disease status, there was no difference in triglycerides between chronically infected and uninfected Amakihi. So it seems that nutrient levels are not impacted by that chronic infection. There was, however, a difference between breeding and non-breeding birds. This could be because of the energetic toll of breeding. So triglycerides were lower in breeding birds than in non-breeding birds. So perhaps these breeding birds don't have as much time to eat because they're busy incubating or feeding their nestlings, so they're not getting as much nutrition that way. Or maybe they're needing to use up these triglycerides in their body for energy. Next, looking at that correlation analysis between CQ value and triglycerides, once again, there was no relationship between the two. So again, the Amakihi continued to show tolerance to chronic infection. Their nutrient levels are not impacted regardless of the intensity of that chronic infection. Lastly, looking at body condition, I actually did find a difference between chronically infected and uninfected birds in this case. Birds that were chronically infected actually had a higher body condition than birds that were uninfected. My hypothesis for why this is that avian malaria kind of acts as a filter for the birds, where the really poor body condition birds don't survive the infection. And so these birds that you get that are chronically infected are just birds that were better conditioned to begin with. I also found some differences in sex and breeding status. Breeding birds had a higher body condition than non-breeding. This is sort of interesting and kind of goes against the triglycerides trends, but maybe it's that triglycerides don't play the biggest role in mass gain for Hawaiʻi Amakihi, so it might be worth looking into other nutrients for them. This could also be that we're catching them at the beginning of their breeding cycle because they're less active as they're incubating and later in their breeding cycle. And so maybe they've been piling up nutrients to get ready for breeding and we're catching them then. We also found that female birds had a higher body condition than male birds. This is also a kind of interesting trend, but one that I think we will need to retest. Pretty much all of the sexing data we'll need to retest. There were some discrepancies in the sexing data, but we're currently working on genetically sexing all of the birds that we've taken data from for the Ādinahou project. And so in the very near future, I'll be able to rerun all of these stats with more concrete sexing data. So it will be interesting to see if this trend continues to hold true. And then lastly, looking at the correlation analysis, that level of chronic infection, once again, does not impact body condition. So it seems that Amakihi are tolerant on all fronts. Regardless of the level of chronic infection, their physiology is not impacted. So in summary, there were no differences in hematocrit, triglycerides, nor oxidative damage between chronically infected and uninfected birds. Mass was slightly greater in chronically infected Amakihi than it was in uninfected Amakihi. And hematocrit, triglycerides, oxidative damage, nor mass showed any relationship with the level of parasitemia indicated by CQ value. So there were some limitations to the study that I'd like to discuss. I went into a couple of them a bit, but first of all, the study operates largely on the assumption that Amakihi don't clear chronic infection. So if an Amakihi has acute infection and chronic infection following that, they have that chronic infection for the rest of their life. This hypothesis hasn't been disproven, but one thing the Ādinahou project is looking at is if there are instances of birds going from being chronically infected to uninfected and getting rid of that infection entirely. And that would make us need to kind of reassess these results. There's also no consensus, as I mentioned, between on the cutoff of CQ value between chronic and acute infection. And so getting that information, determining where that cutoff is, will be really useful for studies like this. Another thing the Ādinahou project is working on is looking at slides from Carter Atkinson's studies where acute infection was determined and seeing how the CQ values measured with qPCR compared to those slides. So we can get a better idea of where that cutoff is. We also don't quite have enough data at this site for survival estimates yet. A lot of questions came up for me while looking at these results on the survival of these birds. But it's something we're working towards. I think we're about 2 years in. And so 1 more year, we'll be able to get survival estimates using that mark recapture effort. And so stay tuned, but right now, those questions remain unanswered. I also mentioned the discrepancies in sexes. We're working to resolve that by getting that genetic sexing data, and we'll rerun the stats once we have that. Another bias in this data set is that there are more uninfected than chronically infected Amakihi. This is to be expected, but having more birds, getting samples from more birds will increase the power of this study so that bias doesn't have as much influence. So where do we go from here? Some future research ideas are to look at the effects of disease on other contributors to fitness. So survival, as I mentioned, we're working to get towards getting those survival estimates. Also activity levels. Part of this study was also equipping some adult male Amakihi with radiotelemetry tags. And so something we're interested in looking at is if there is a difference in activity levels or movement patterns between chronically infected and uninfected birds. And also reproduction. There was one Kilpatrick study back in 2006 on reproduction in chronically infected Hawaiʻi Amakihi that found that males with that chronically infected, or pairs with that chronically infected male had higher nesting success. But it's been a while, and their nesting studies are difficult, notoriously difficult. So this would be something worth looking at further in the future. Another big topic of study in this field right now is determining the factors that make Hawaiʻi Amakihi more resilient. They are the main bird that has been able to persist even in areas where the infection rate is really high. And so finding out what factors it is that makes these birds more resilient can be used to help our other honeycreepers as well. So there's a lot of work being done to look at their genetics, if that's what's causing this resistance, the food they're eating, their gut microbiome, antioxidants that they're getting. So really it's an all hands on deck effort looking at all kinds of things in these birds to see what it is that's facilitating this resilience and how we can apply it to help our other honeycreepers. I'd also be really interested in looking at if physiology can predict the survival of acute avian malaria. This is something we'll be able to do once we have those survival estimates, but this would answer questions like why are birds with chronic infection better body condition than those that have never been infected. I think it would also be worthwhile to investigate the factors that go into oxidative stress. ROMS that I measured is really just giving you the net value of oxidative stress, but you have things on either end. You have these pro-oxidants in the body and antioxidants working against that happening at the same time. So seeing what's happening on either end of this reactive or oxidative damage and seeing if there is more pro-oxidant activity and they're offsetting it, or there's just not more pro-oxidant activity would be really interesting. And lastly, just a question that came up for me was looking at the physiology over the breeding period. I think it would be really interesting to investigate that phenomena of reproductive anemia further and see if that is a factor for our birds here in Hawaii. So in conclusion, there are no apparent physiological costs to chronic infection in this population of Hawaiʻi Amakihi. And it's so rare that we get to deliver good news in the bird world. So I'm really stoked to be able to tell you all this today. And also based on mass, chronic infection or chronically infected Amakihi might even be healthier. And this could be because the unhealthy birds die from infection and so aren't in that population of chronically infected birds. It could also be that healthier birds are more likely to get infected. Maybe they're flying around more, maybe they're more likely to encounter a mosquito for whatever reason. And I also found in this study that Amakihi are tolerant of chronic malarial infection. Regardless of the level of infection or parasitemia in their blood, their physiology was not impacted. So what does this all mean? This is one of the first studies to assess the long-term impacts of avian malaria in a wild population in Hawaii. There was that one other Kilpatrick study that looked at reproductive success, but otherwise there has been nothing before this. So it's really useful to look at those long-term consequences. There's been a lot of study on the acute stage of infection and how birds do during that. But if they continue to have this low level of parasitemia, potentially for the rest of their life, the acute stage is not the only thing impacting them. And there could be consequences past that that haven't been captured. So I think it's important that we look at those. It's also important to understand what makes Amakihi so resilient to help other species. And so it's great that we found that after Amakihi survive acute infection that they do pretty okay. because then if we can help other honeycreepers survive that acute stage, maybe the same will hold true for them and they won't have those long-term fitness impacts. And lastly, this is another testament to the resilience of Hawaiʻi Amakihi. I think that ʻōlelo no eau, ka'u makaha, ka'u of the fierce fighters applies just as much to the birds as it does to the people. So there are so many people to thank. This project really defined it takes a village. First, I'd like to thank my advisor, Pat Hart. He's the reason I came here to Hawaii, and he's been so supportive of me in all my bird-related endeavors since I came here, so I'm really grateful to have worked with him. Also to Christina and Evan Paxton, who are both on my committee, but were also my main collaborators for this project. Thank you so much for bringing me onto the Āinahou project. It's a really meaningful project, and I've learned so much from being there. I've learned so much from you as researchers. So I'm really grateful to have worked with you and have had this experience. And I hope to continue contributing to the Āinahou project moving forward. And also to Susan Jarvie, you've been a huge help on the physiology component of this for letting me store all my samples in your freezer and take up space in your lab. And thank you for all your input throughout this process. It's been really helpful. I also must thank all the USGS volunteers that contributed to this project. This is as much their project as it is mine. Carly Stein, Mylise, Wade, Lily, and Makoa, who was a pipes intern. They all were a huge help in running qPCR, processing these samples, extracting the blood. I would not have been able to do this project without them. So I am so grateful to them for all of their contributions. I also want to thank everyone who came out banding with us. Just to name a few: Josie, Braxton, Paulo, Lauren, Noah, Amanda, Mia, and many more. Thank you to everyone who came out and helped collect data for this project. I also want to thank Anne Tanimoto Johnson, my lab manager. You have been so supportive of me. Anytime I need something, she's on it right away. She contributed a whole bunch of pictures to this slideshow, but also you've just been a huge support for me throughout this whole program, so mahalo. I also want to thank Shushu and Zara from USDA. They were really, really helpful in doing all of my physiology analyses. I needed a specific instrument to run these plates, and they had it, and they were extremely generous with their lab space and resources. So thank you to them for allowing me into their lab to do these analyses. And lastly, I must thank my TCBES cohort members and the professors that I've had here. They've been such a huge inspiration to me and have really supported me a lot through this process. I also especially want to thank Becky Ostertag. You've been such a support for me throughout this whole process, through the whole 3 years. And I'm really grateful to now be working for you. It's really awesome. Oh, and I also want to thank the American Ornithological Society, as they funded this largely along with USGS. But all of these organizations have contributed hugely. And I also want to take a moment to thank all my friends and family who have been such a massive support to me through these last 3 years, whether they're here in Hawaii or many, many miles away on the East Coast. I think these last 3 years have been 3 of the most difficult, but also most joyful and growth-filled years of my life. And so I'm really grateful to everyone who has supported me through all of that. I'm not gonna cry. And especially to my parents, Paul and Val Stierhoff, for always prioritizing my education, even when it makes me move across the world from them. I'm so grateful for their constant support, and to all my friends and family. And lastly, I would be remiss if I did not thank the Manu, the Hawaiʻi Amakihi. This study is by them and for them. They are the main contributors to this project. And I'm so grateful to them for serving as a beacon of hope for other honeycreepers and for their resilience. And I think as much as I try to say I'm not a bird person, my face every time I look at an Amakihi kind of gives me away because I really do adore these birds. And it's been one of the greatest privileges of my life to get to work with them and get to know them and their goofy, strong personalities. So mahalo to them for making this project happen. And here are the many, many references. Keeps going. That's that. So mahalo nui everyone for being here today, for listening, and I'll be happy to answer any questions you have, and also feel free to reach out to me over email if you have any questions that you'd like to ask that way.